let's begin. So, also, I sent 2 emails yesterday from Jupiter. Did everyone get 2 emails? So there was one about how to access the homework, and there's another one about the fact that the website is up, which I already posted the blank for quiz 1 and the answers to quiz 1. And in the same location, I'm going to post the blank and the answers for this one as well. So like I said, the first quiz is a diagnostic. It doesn't really count. It's just for me to see where you are. If you go through the diagnostic, what I would say just as a general rule of thumb, whenever I post the answers, you don't go straight to the answers. You try to look at your thing, see what you got wrong, and try to do it on your own before you look at the answers. So there is no shame in seeking help, but you want to do that after you actually try very hard to solve the problems on your own. So whenever I post solutions, don't just look at the solutions. Actually try the problems yourself, make sure you actually understand where the answer is coming from. Hopefully that quiz wasn't too bad. Was that okay? No?
No, I'm going to be honest.
Okay, well hopefully over time they'll get better. But that's kind of what they'll feel like usually. So you'll notice that I asked you about some general concepts and then I asked you about some specific problems. Pretty much every quiz is going to be like that. And you'll notice that the bonus section is stuff that we haven't covered yet. That's also going to be typical. Things that I'm about to cover, I'll put in a little bonus section just as a reward to anyone reading ahead. They can probably pick up some extra points. That being said, let's actually just move on. So this is probably not something that I would generally talk about at this point, but your textbook brings it up pretty early, so I'm going to talk about it. Because if I give you homework now, chances are it's going to show up. It's called average rate of change. I will talk about it at some point later on, but just to introduce the idea and talk about how you'd actually go about computing something called the average rate of change. I want to just talk about that very quickly. Okay, so let f of x be a function. The average rate of change of f of x on, it has to be a certain interval, an interval, say AB, is a measure of how much f of x changes in relation to x specifically. So let's say we have our function. And it's doing whatever, right? So that's your f of x. Okay. And I'm worried about an interval AB, some specific interval. Right, so I only care about the piece of the function that's within this window. So the average rate of change is on average, how much did the y value change over that length? And how we define that is in the following way. We connect these 2 points with a line. That's right, I heard someone whisper. It's called a secant line.
Yeah, I did. Oh, maybe I'll get that.
So that's what it's called. It's called a secant line. You connect 2 points on a function, 2 separate points by a straight line. Such a line will be called a secant line. And the average rate of change, let me call it because I don't want to. sometimes I usually write out average a little bit. Average rate of change is going to be the slope of the secant line. On the interval. I want you to notice that this is going to be measured, sometimes it's called delta y by delta x, and this is the change in y. So that's how much the y values change, and this is called the change in x. So let's say I gave these guys y values, this will correspond to y values f of a. That corresponding y value is f of b. So that will actually give us, what is the change in y? How did the y value actually change? Well, it's the difference between these two numbers. In fact, you measure a vertical distance by taking the higher distance minus the smaller distance. So f of a, f of b minus f of a, that's your change in y. And your change in x, so at one point your x value was a, then it ended up at x equals b. And you can measure the horizontal distance, the horizontal change in x by this minus that. And so that's b minus a. And so you can have the average rate of change of f of x is f of b minus f of a over b minus a. And sometimes for shorthand I might call this f average, just because I'm lazy to write out average rate of change all the time. So that's the equation. Find the difference in the y values and find divided by the difference in the x values. Now you'll notice here we can do a slight change in notation. Suppose, and I'm looking at the same function now, let's see if I can recreate it. So it's the same function, but now we can actually label things a little bit differently. Let's say I start this, it's the same point that I care about, the same point that I care about, and still just a line connecting the two. So let's say I started by thinking of the first point as some x value where I'm currently located at, and then the next point is some other x value where the distance between the two x values is traditionally called h. So this x coordinate is going to be f of x plus h. The corresponding y values, well, that would be f of x. Corresponding y value of this guy will be f of x plus h. And now if I find the slope, the average rate of change is going to be the difference in the y values, y2 minus y1, over the difference in the x values, x2 minus x1. You will notice that the x's will cancel, and you would end up with f of x plus h minus f of x over h. That guy looks familiar. That's the difference quotient. This is where the difference quotient comes from. It's the slope of a secant line. It's also a measure of the average rate of change of a function. But it's worth mentioning, usually if the situation calls for the average rate of change, like you see that phrase, find the average rate of change, usually you want to think of it as this way. And so we use this version of the formula. There's going to be another time where we prefer this version of the formula, but for average rate of change, when that is the point, that is the goal, it's this guy here. So let's actually just do an example of us finding it, and then I'll talk about it a little bit more. So in terms of average rate of change, I will ask you a problem, just pretty much straightforward. Something like this. Let f of x equals, say, x squared plus 1. Find the average rate of change of f on the interval, let's say 1, 4. So that's circle. Interpret. So you see a problem like that shows up on a test or a quiz. Here's how you would actually go about solving it. Notice here that your a value is always the left end point of your x coordinate, so a is 1 in this case, and your b value is the right end point of the coordinate, so those will be given, right? So I could say, give you as an interval like this, or I could actually say something like 4x between 1 and 4, or something like that. Notation. But that would be like a problem, right? So how you'd go about doing this? Well, you realize that f average is f of b minus f of a over b minus a. And that's just a formula we should know now. You should know that by heart. I'm not going to tell you that formula. You have to know that formula. So that is going to be equal, in this case, f of 4 minus f of 1 over 4 minus 1. How do I find f of 4? Well, you plug 4 into the function. So that's 4 squared plus 1 minus 1 squared plus 1 all over 3. So that's going to be 17 minus 2 all over 3. Or in other words, that's going to be 15 over 3, which is going to give you 5. And so you can say the average rate of change is 5. Now, how would you interpret that interpretation? If someone tells you the average rate of change on this interval, interpretation, is 5, what are they telling you? Basically, they are saying this. For every 1 unit x increases, the y value will increase by 5 units on average. That will basically be your interpretation. It's kind of telling you how does the y value change in relation to the x value. Every time the x moves over by 1 unit, on average the y value is going to jump by 5 units. Now, it does not have to actually jump by 5 units on average. So let's say this is, it does not have to jump by specifically 5 units because that's not actually true in this case. So let's say here's the 1 and over here is the 4. Notice that your f of 4 is actually 17, your f of 1 is actually 2. Now, technically, if you were to measure like a line connecting those 2 points, you realize that once you hit 2, your x value moves over 1, you'll realize that the y value will jump to 7 if you're on that blue line. So it's not necessarily on the function, but we don't really care about that. And once you jump to 3, it's going to jump by another 5 units, and that's going to jump to 12. Once you jump to 4, it's going to jump by another 5 units to get to 17. So on average, while in the middle, the function is not actually doing that. On average, right? So if I look at the overall on that interval, if I measure based on this line, the secant line, every time I move over 1 unit, I jump by 5 units on the secant line. So that's called the average rate of change. So overall, you can see once my x value covers a distance of 3, my y value will cover a distance of 15. So roughly 5 units for every 5 units of increase here for every 1 unit of increase there.
I can do a slightly different idea here. So let's say another example, your f of x is 4 minus x squared. Find the average rate of change on the interval. Let's do the same interval, 1, 4. So what I would do is your f average is going to be f of b minus f of a over b minus a.
Whenever you learn a new topic and there's a new formula, one of the tricks is just write down that formula all the time. Every time you're doing a problem, you write down the formula. Eventually you'll remember it. So this is f of 4 minus f of 1 over 4 minus 1. F of 4 in this case would be 4 minus 4 squared. Minus f of 1 would be 4 minus 1 squared. All over 3. So that's 4 minus 16, that is minus 12. 4 minus 1, that is 3 over 3. Now what's going to happen? You'd have negative 15 over 3. This gives you minus 5. Now what would be the interpretation of that number? Well, the interpretation here is for every 1 unit increase in x, there is a 5 unit decrease. Right? So the decrease comes from the fact that you have the negative sign here. Right? And this is something that we're going to come back to. We're going to, in a lot of ways, we're going to think of increasing as being positive in some sense and decreasing as being negative in some sense. And we're going to make good use of that idea pretty soon. There's a 5 unit decrease in the y value on average, right? Because the function itself might not actually behave that way, but if I'm kind of approximating the function with the secant line is going to behave that way. And if you want to see a picture here, you know what this guy looks like. I believe this was actually a function also on quiz 1, where actually I see what this looks like. So we can have 1 and actually because this actually intersects where? This is at 2, so my 1 is here, my 4 is actually out here. And so, it wasn't on the scale on me, let's see, I do that. So what I'm doing is I'm connecting these 2 points with a line, connecting here, connecting here, and the corresponding y value for this is minus 12. Corresponding y value for that is 3. You'll notice that the slope of this line here is going to be negative 5. And you'll notice, like, on average, for every 1 unit distance I move that way, I'm moving 5 units down that way. And so I can describe that as an average rate of change of minus 5, right? On average, when x changes by 1 unit, y will change by 5 units in the negative direction. And eventually we're going to put some interpretations even on that, but for now, that's kind of what I want you to get away from this idea, the average rate of change. It's a very important idea. Introduced a little too early for my taste, but it's an important idea nonetheless. We will come back to this idea, but that's a thing. You might see a problem like this in your homework because your textbook actually introduces this idea very early on in the page. late chapter 1, early chapter 2, something like that. Any questions on that idea? That's pretty much what you do. Average rate of change, use that formula, is the idea. You should also know how to interpret it, whether it's positive or negative, know the interpretation. And yeah, that's it. Now, this is an applied calculus class, after all. So we should be talking about calculus, and we haven't been talking about any calculus yet. But let's actually begin by asking the question, what is calculus? Right? So we're going to start talking about calculus pretty soon. Well, what is it? What is it? How many people did calculus before? Yeah, what was it? What is it?
There's a lot of like behavior of functions, if that makes sense.
Okay.
Like derivatives.
More specific? Because a lot of math is about behavior of functions. You learn about behavior of functions in pre-calc and algebra. In calculus specifically, what behavior are we talking about? Any things that showed up commonly in calculus? Derivatives?
Mhm.
Remember that name? It's the study of derivatives. Anything else you study in calculus?
Limits.
Limits, yes.
Is that a limit? Same thing. Integrals.
Integrals,
Oh, we're on fire.
and their applications. Right? We studied the derivative, integral, and how we apply them to solve real world problems or whatever, right? And so people who haven't taken calculus before still are probably confused. Oh, so what is it exactly? Okay, so let's actually make that a little bit more precise. Calculus actually breaks down into two branches. Right? So there are two main things that we want to think about when you're talking about calculus branches. So the first branch is called differential calculus. And here's where you study derivatives. What is a derivative? Why do we want to study them? Well, the goal in studying a derivative is to solve something called the rate problem. Okay? So there's a type of problem that we call the rate problem, and the derivative is a mathematical tool that we use to solve that problem. Basically what the rate problem is, in a very general, broad sense, is figure out how fast something is changing. What thing? Anything. That's kind of what the rate problem is about. How fast is something changing? Now, you're all alive long enough to know that life is about change. Everything changes, right? It's law of thermodynamics. Everything gets worse. It's a very pessimistic way to look at the world, but there's a probabilistic background to that. But yeah, everything changes. Nothing stays the same. Nothing is stagnant. The sun rises, the sun sets, tide comes in, tide goes out, right? Things keep moving, right? Now, if we want to really, dominate our environment and try to figure out how to apply these things, figuring out how fast they change is going to be very important, right? How fast is the tide coming in? If I can predict how fast that's coming in, I know how to deal with the shoreline, right? I know how to build structures around the shoreline or whatever, right? I know when am I in danger of certain things happening, when am I not, right? So knowing how fast something is changing is a very important thing to figure out. That's what a derivative does. It helps us figure out how fast something is changing, right? And that is called the rate problem, right? Now, there's another branch of calculus. This is called integral calculus. Right? Now, this is the study of integrals, this other guy right here. Now, What is an integral? That's a mathematical tool to solve a certain other kind of problem, to solve what's called the area problem. Now, what's the area problem? Basically, figure out how much space something takes up. That's the area problem. How much space is this thing over here taking up? Now that could be in terms of an area if it's some sort of two-dimensional figure. Could be a volume if you're in 3 dimensions. But just figuring out how much space something occupies is the area problem. And of course, if you have a nice shape, a rectangle or a circle or a triangle, you can figure that out pretty easily. But what if you have something irregularly shaped, right? How much space did I just cover on the blackboard, on the whiteboard, right? How much space is inside this weird shape? Is there a formula for figuring out what the area of that shape is? And even if I figure out a formula for that, someone can make the shape a little weirder by adding a little notch on it or something, right? So figuring out how much space irregular objects take up is the area problem. Can I figure out how much space? That's also something that's important to figure out. You can imagine that if you were like a farmer and you have a plot of land and the government is charging property taxes based on how much land you own, you're like, well, how do you know how much land I own? It's a very weird shape. How do you know? How do I know that you're not overcharging property taxes? More importantly, how do I know to stay silent if you're undercharging? Right? Like, how do I know how much land I actually own? It's a very weird shape. This is the area problem. Figure out how much space something takes up, right? So calculus has these two branches. They study two different things, the rate problem and the area problem. We want to know how fast is something changing. We also want to know how much space something is taking up. And it turns out that it seems like very big, heady problems. How can you even come up with a way to actually talk about that? Like anything, something? Like any shape, really? But we've actually known how to solve these problems for millennia, literally thousands of years. Like there's evidence that Archimedes in 300 BC was doing calculus, right? So we've actually known how to solve these two things for a long time. Here's the new idea, and by new, I mean 300 years old. It's about 3 centuries ago. We actually figured out that these two things weren't actually separate at all. They're actually connected. It turns out that figuring out how fast something is moving is kind of the same as figuring out how much space something else takes up. It's like you're solving the same problem from two different angles. It turns out that these two are very intimately connected. These are connected. In fact, figuring out one problem is kind of like figuring out the other problem in reverse. It's connected by a very important theorem called the fundamental theorem of calculus. And that's why we're here. That's why calculus class exists. 300 years ago, Isaac Newton and another mathematician in Germany called Leibniz figured out that these two different areas of math, they're actually the same thing. If you know how to solve one problem, you automatically know how to solve the other if you just kind of turn it around. And I mean, Isaac Newton's teacher, a guy by the name of Barr, also had a lot to do with that. But basically, these are the two same problems. That notion is calculus. We can study these two things, and when we study them together, connected by the fundamental theorem of calculus, we say we're studying calculus. That's what it is. That's the point. Figuring out how fast something moves and how much space something takes up. In fact, this was the question that Newton was worried about. Someone asked him about how fast the planets in the solar system were moving, and he was like, I don't really know. He went home and invented calculus to figure it out. How to answer that. Oh yeah, I can predict Mars is going to be here, right? And he realized that he actually used a lot of tools over here to help over there. And that's what we're doing here, and we will start that next time. That's where we're going. And I will see you guys next time.